Good morning, students. Welcome back to digital electronic class. Before proceeding for further class, let's take a previous class overview. In the previous class, we have discussed the problem based on your manipulation of your data by using the mean term and max term. How do we convert the mean term into max term and the max term into mean term? That part we have covered, and we have just take a introductory part of KMap. That is nothing but the kernel map. We have discussed about 2 variable, 3 variable and the 4 variable. In today's class, we are proceeding with the same concept but little bit in detail. So let us come to the topic. In today's class, we are proceeding with this kernel map, or in short we call it as KMap. Before proceeding these things, in the previous classes, we have discussed the manipulation of algebraic function, that is the Boolean function, by using the truth table method, by using the manipulation the data by using gate level method. These things we have covered. In today's class, we are going to deal with the KMap. So in this, the first thing what we have discussed is the algebraic manipulation by using the data. This all we have done, these kind of problems by using the loss. What is the loss means? The Boolean loss, the Boolean algebra loss we have discussed, and we have talked about the De Morgan's loss. So based on that loss also we have done numericals. So that only the point I am explaining over here. Here I am saying I am using the algebraic manipulation by using the loss. So that already we have discussed. So that is the first thing we have covered. Next we have done the examples. So by using the examples we come to know how to minimize the data by using the examples. Like we have talked about x bar y bar z plus x bar y z plus x y bar. What is a common term in that? We apply the formula y plus y bar is equals to 1 and we found the value. So this 3 terms has been reduced to 2 terms with less number of literals. So what is the meaning of the literals? So literals we are saying, literals means if you do have x, y, z, so these are how many literals are there? There are 3 literals in it. So these 3 literals you try to minimize. So in order to minimize the number of literals, we are using the Boolean loss or by using the De Morgan's loss. So these kind of problems also we have talked about, and these examples, everything we have seen in the previous class. These all problems, how do we convert mean term into max term into mean term. So we are not going into detail about that. Today's class, the main questions we are covering is De Morgan's loss, sum problems. How do we convert the sum products into the product terms and product term into sum terms? Instead of using the mean term and max term numericals, here we are using the expressions. So here they gave one expression, f1 is equals to, so they gave f1 function. So what is f1 value they gave? f1 is equals to x dot y bar with whole bar into y bar plus z whole bar. This is the question they gave for f1, right? So in this, what actually we need to find? They asked to simplify the following Boolean expression and note the Boolean or De Morgan theorem used at each step and put the answer in sum of product form. So what is sum of product in the sense? What is actually? This is what? These two are a product of sum. The question is in POS. How do we are saying it is POS form? Because first we are multiplying, that is nothing but product. Then we are adding. So what is addition means? Sum. Then it is considered to be the product of sum. So we need to write the same question in product of sum form. So we need to do that by using this question. So first thing, f1 they gave, f1 is equals to x dot y bar. Again bar is there, then whole bar of y bar plus z. So first thing, you should recall the formula of, what is the formula of this thing? We should recall the formula of De Morgan's. So what is the De Morgan's law states that? If you had a plus b whole bar, that you can modify it as a bar into b bar. That is the first law. The sum terms can be written into product terms. So if you had the whole complement, if you want to write in separate form, we can write in this way. Or else, if you do have a dot b whole bar, we can modify it as a bar plus b bar. So here we do have product term we are converting into sum term. So these are actually, this is the nothing but like a formulation of your De Morgan's. So by applying De Morgan's theorem, we can simplify this question. How do we are simplifying? First thing, first we are taking the function f1 value, then second thing what we are doing, we are applying first formula, dot we want to write in addition. So what I am doing, this bar and this bar I am separating. By which formula? This formula I am applying. What is the formula in this? A dot b whole bar can be written as a bar plus b bar. So what is a over here? A is the whole function, whole expression. X dot y complement with one complement, that is as it is. This dot will make it as plus and again this one. So this is a bar plus b bar, that we modified by applying De Morgan's law. Likewise, further what you can do it, you can apply Boolean expression of that law. What is that law statement of that one? If you do have a double complement, we can write it as a. That is another way. So a double complement I can write it as a. So for that what I am writing, this as it is x dot y. See, x double complement. So what is x double complement I can write? I can write as x. Similarly, y 3 times complements are there. 3 we cannot remove it. What we can remove? We can remove 2. So that what? It is y 1 complement. So double complement is gone over there. Similarly for this, y double complement into z is there. So what is y double complement? It's y as it is. Here x into y complement into z complement as it is. So your function, how do we mention x y complement plus y z complement? That means your complete function f1 whole, what is that? It is product of sum, that we modified into sum of products by applying De Morgan's law. So that's the way you can do some problems. We'll solve these kind of questions in chalk and talk method. When we go for the more problems on this thing, I'll explain you. But as of now, you remember when you had the questions to convert your product of sum into sum of products, we can do in this way. Next. So next topic is about the canonical form and standard form. So what is the canonical form and standard form? It's all about converting your mean term into max term into mean term by applying the complement function. So by applying some sort of complement function, we do mention this canonical and standard form. So in this thing, first would be mean term. So what is the mean term means? It's a standard product in which you are using and term consists of all literals in their normal form. That means if you had like 1 1 0 0, if you had two variables, what are the two variable combinations? 0 0 0 1 1 0 and 1 1. So how do we mention? By using the literals like this: x bar y bar, x bar y, x y bar, x y. So this is how your mean term representation can be done. So likewise max term. So what is max term means? 0 means x, 1 means x bar. So it's quite reverse for max term, which we are taking for mean term. So here total combination would be 2 power n. So 2 power n would be the combination. Irrespective of number of bits, we'll completely see how many mean term and how many max term, and we'll take that combination by taking this formula as 2 power n. So by using this thing, we can convert your number into respective mean term and max term. Now, this thing also we have discussed in the previous class. This is about discussion of mean term and the max term. So mean term, likewise we'll mention 0 means x bar. Here 0 means x. So this is written in multiplication form. Here it will be written in addition form. So this thing also we have discussed in previous class. Excuse me. Next thing, we do have function. How do we write truth table? So this, in the second lecture of your digital electronic class, I have talked about if they gave the function, they asked to write by using truth table, how do we mention? So for doing this thing, what we are taking, suppose they gave question x bar y bar z plus x y bar z bar plus x y z. So what is x bar y bar z means? X bar y bar z would be what actually? So the question over here, what they gave? They gave f1 is equals to x bar y bar z plus x y bar z bar plus x y z. So what is the meaning of this thing? X bar means 0 0 1. This is 1 0 0. This is 1 1 1. So what is 0, 0, 1 means it's mean term M1. This is mean term, what is the value? M4. This is mean term M7. So this means I can write summation of 1, 4, 7. So this is your Boolean function F1. So we do have this F1 value. We need to write its truth table. Then we can ask you question, write the truth table of this given function. So what we'll do? First it's 3 variable. We'll write all the combinations starting from 0, 0, 0. Maximum would be 1, 1, 1. So as per our question, what is there? Mean term 1, mean term 4 and mean term 7. For these values it should be 1. For remaining value it will be 0. So that's how this F1 function is written. Likewise we do have another F2, that similar way we can do it. So the main thing what you need to understand is mean term M1 is 1. As per the question, 1 we do have, it's quite not visible there. So we can look it here, 1, 4, 7. So 1 should be high, 4 should be high and 7 should be high, because these are the present terms in the Boolean function F1. So that's what here M1, M4, M7, 1, remaining will be 0. Next. So now how do we write the complements? The complements means what? For example, if you do have F1, this term, if you want to write complement of it, F1 complement, how do we mention? Summation, same thing. 1, 4, 7 is there, remaining terms we don't have. So what we'll do? We'll write 0, 1 already is there, 2, 3, 4 is there, 5, 6. That means whatever terms are not there in F1, that is the complement terms, F complement. So this sum term what we'll mention, if you want to write in terms of product, they'll write pi of 0, 2, 3, 5, 6. So they can ask to write this SOP into POS. So we'll write like this, or mean term into max term will represent like this, or they'll ask to write the complement. So this the way we'll mention your function F1 in terms of all these things. So that's how they did some problems. So we already covered this thing. If they gave F1 value like M0, M2, M3, M5, M6, the same function you need to write in terms of complement. So what we'll do it, we'll try to write its complement value. So 0, 2, 3, 5, 6, we'll write the complement, we'll write with respect to its terms. So that's how we'll convert the function. Next thing, sum of products, this we covered, product of sum, this also we have done, and writing the variables. Next, main important thing is that how do we write the functions in canonical form? So how do we write that canonical form? So to do this thing, we'll take the function f of, they gave different functions like this. We want to write its complement. So that means similar to this thing, converting F1 to F complement or F1 to product term. That questions I have mentioned some problems over here that you can make a note of it and you can practice these questions for your reference. For doing these things, you take the questions like F is equals to sigma of 1, 4, 5, 6 and 7. So for this thing what you'll do, you'll try to write its respective term in terms of complement. So what we are doing, we want to write the function, we wrote it, whatever not present in this, like 0 is not present, 2 is not present, 3 is not present, we wrote it. So by applying De Morgan's law or by using the things what we can write, this complement you want to write. So how do we mention that complement of this? M0, M2 and M3. So 0 indicates what? It's a product term of 0, 2, 3. So that you can modify by taking this terms. So how do we write it? So that same thing, the sum term is now it's modified into product term by mentioning the pi. Next thing, how do we mention that one? That is the way we can mention it. So this is what sigma of m. So sigma m of this whole thing, if you write the complement of that one would be what? Pi of m. What is not present in this? Two functions. So since starting from 0, we don't have the mean term 1. So that is present in max term. That's what it's 1. 2 is there? Yes. Do we have 3 mean term? No. So we need to mention 3 over here. So this is how your M1, 1 and 3 will be written. Similarly, we'll take one more problem in this. F of xy plus x bar z. So the question is, they gave the question, we need to write what is that value for it. How do we write this thing? We'll do here. So the question of F1 would be, F1 is equals to xy plus x bar z is there. So what is not present in this? Xy we don't have z. So what we can write for this? Z plus z bar. Here what is there? X bar z is there, y is not present. So we can write y plus y bar. So what is the value of it? X plus x bar is 1. Like this, z plus z bar is also 1. So y plus y bar is also 1. Why there is need of changing this thing? Because we want to write in sum of product terms. So directly we cannot write 2 variables. If it is there, then we can do it. But here is 3 variables. It's function of x, y and z. These 3 variables must be present in each function. So we don't have this thing. X, y is there, z we don't have. So here x, z is there. We don't have y. So we need to write this thing. So to do this thing, we multiply it first with z, second with y. So we got, what is the value for this? X, y, z plus x, y, z bar plus x bar, y, z plus x bar, y, bar and z. So what is x, y, z? It is 1, 1, 1, m7. Here 1, 1, 0, it's m6. Here 0, 1, 1, m3 plus 0, 0, 1, m1. So that's how you got this 1, 3, 6, 7. So we got this terms 1, 3, 6, 7. So that is in sum of product, that is in mean term. So we need to write its max term. That means 1, 3, 6, 7 is there. Apart from this, the number which is not present in mean term is there in the max term. So 1 is there, 0 is not there, so 0. Then 2, already we had 1. Then 3, we don't have 4 and 5. Mention it. So this is mean term, that is a representation of the same function in terms of max. Standard form representation, this thing implementation also we have done by using the vertical approach. Here also they gave functions by using the horizontal approach. So we'll do these problems in chalk and talk method. I'll take the questions, I'll explain you the logical diagram for it. How do we mention that functions? So the question here is, they gave 2 questions. You see students, so we did some problems by taking vertical approach. Here we have the questions for horizontal approach. In the question what they gave, see this question, AB plus CD plus CE. So they said multi-level implementation. So what is the meaning of multi-level implementation? So we need to write directly the horizontal form, that is a standard form. In standard form we are using which gates? AND and OR. In the question, when they ask to solve it, they'll specifically mention that solve the questions by using AND and OR. That means we should use only AND gate, we should use only OR gate. So here AB, so we are taking 2 inputs AB, we are connecting one AND gate. Likewise we do have CD. Just a minute. So see students, so we are continuing with these problems. AB plus CD plus CE they gave. The question is converting into standard form. So here the question they can ask you exclusively, they can mention in the question, implement this function by using AND and OR logic. For doing this thing what we'll do, we'll use only AND gates and OR gates only. Apart from this we'll not use any NOT gate or any exclusive OR, exclusive NOR, anything we won't use it. So here AB, we connected 2 inputs with this AB, then CD we connected, then we see CE. So all separate we have given because it's a horizontal approach. Here we are designing horizontally. So this is AND gates, we need to go for addition. So we connected with one OR gate. So this is how this function implemented by using AND OR approach. So likewise we do have another function. So here what we are doing, we are taking this function y complement. So this is directly we took y complement plus x y. So this is your x and y. This is one more AND gate plus x complement y z complement. So there are 3 inputs. So x complement y and z complement. So these 3 functions F1 we took. They give what? Only this question also implemented. So the question is to implement by using your sum of product. That means only AND gate and OR gate. These 2 gates only we should use, AND and OR approach. For that AND gate and OR gate we use and we have designed. So this is how your implementation of this function F1 and this implementation of this function F2 and this one F3. This is your F3. So here also AB plus C of D plus E. So for this what we have taken? We have taken AB, that is one AND gate. Next C of D plus E. D plus E means what is plus indicates? It's what? OR gate. So that's how we have taken D plus C, we connected one OR gate. So after knowing this D plus C and AB, next thing C we should multiply with D plus C. So C we are multiplying with D plus C, answer we got one more AND gate. So after knowing these two AND gates, we need to add. So in order to do addition, we connected one more OR gates. That's how this function has been implemented in this way. So after knowing all these things, next topic what we are going for is the KMap. So what is the KMap is all about? Is about the Karnaugh map. The main criteria of getting into KMap is that we had lot of complexity in the digital circuitry designing. So in order to remove this, in order to overcome from these kind of complexity in digital electronics, so we are proceeding with Karnaugh map or KMap. So in this, the first thing what we should know, it is nothing but like a graphical display. So what is the use of graphical display? It is easy for us to get without any simplification the answer for it. So that's how we are saying it's graphical representation of fundamental products in a truth table format. That means whatever truth tables we are writing. So till now we have seen, right, some problems of truth table. So whatever we are writing the truth table, so it is easy for us to write this graphical representation. Second point, it says that instead of using the Booleans, algebra simplification techniques, that all laws of what are the laws we have seen? We have seen De Morgan's law, we have seen associative, distributive, commutative, observation, idempotent laws. All these laws we have seen, like A plus A complement is 1. A plus B of C can be written as A plus B into A plus C. Likewise, we have seen X plus Y whole complement, that can be written as X complement into Y complement. Likewise, we have seen lot of questions, lot of formulas in order to solve the questions. So we don't want required all those formulas in KMap. In KMap directly from the graph itself we will get the answer. So that's how they are saying, instead of using these all, directly we'll get the answer from the graph. That is Boolean statement of or truth table in KMap, it's easy to solve. Likewise, the map methods are efficient way of minimizing the Boolean functions. Excuse me. Next, the map method was first proposed. The one who described this is nothing but the Vecchi diagram. It is by E.W. Vecchi, a person who has explained this thing in 1952. In 1953, the Morsi Karnaugh has actually proposed this method. Then this is considered to be the Karnaugh, the name of that person, or in short we call it as KMap. So what we know by how do we construct the KMap? So construction we have seen for 2 variables, 3 variables and 4 variables. So that 2 variables, how do we construct? The first step would be we need to represent with the help of square boxes. So E square box 1, mean term or max term. Next, it can have 2 variables. So 2 variables would be 2 power n, 2 power 2, 2 power 3, 2 power 4. So it is, if it is single variable, 2 power 1. That means 2. 2 means what are the binary numbers? Either 0 or 1. If you do have 2 variables, that means 2 power n, 2 power 2, that is 4 square boxes. That means 4 variables. 2 variables, 4 combinations. Likewise, we do have 3. Likewise, we do have 4. So 3 means 2 power 3, it's 8. So values, the mean terms from 0 to 7. So likewise, we do have 4 variables. So in 4 variables, the values are from 2 power 4, that is 16. So what are the mean terms we do have? Mean terms are starting from 0 to 15. Next. So this is the way we have represented your max term and your mean term. So what is a max term means? 0, 0. So 0 means A, again 0 means B in max term. So we can write A plus B. So likewise we do have 0, 1. So 0, 1 means 0 means A. So B means B bar. So it actually has to come A plus complement should come here. Next 1, 0. 1, 0 means A bar plus B. So 1, 1 means A bar plus B bar. This is how the max term will be represented for 2 variables. So likewise, if you don't want to write the max term, we can write like this, right? 0, 0, 0, 1, 1, 0 and 1, 1. So here has to be 1, 0, here has to come 0, 1. Likewise, we do have mean term. How do we mention mean term? 0, 0 means A complement, B complement. 0, 1, AB, A bar B. This is 1, 0, AB bar, and this is 1, 1, AB. So this is how you represented two terms of two variables, three variables. Now this is a four variable. So in four variable, what do we mention? All four zeros. So M0, M1. Then we'll go for folding. M2 and M3. How is it there? So see, 0, 0, 0, 0, it's 0. 0, 0, 0, 1, it's mean term M1. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is how your four variable KMap has been designed. This actually we have seen with the help of blackboard method. I have explained you how do we design this thing. So only here we just want to see the detail about it. How do we design it and how do we construct the KMaps. So this digital logics, this is a summary of what we have discussed, and or inverter or buffer. So these truth tables also we are familiar with these things, and even we have utilized this thing in problem simplification. And the summary of logic gates, how do we convert your NAND, NOR. So NAND, NORs are very important. They'll give the questions to implement by NAND and NOR. We'll do the problems of this one in the next class. How do we implement NAND gate? How do we implement NOR gate for basic gates? So these things we'll see in the next class. So this is our IC. How do we use IC? Actually, where these all logic gates are used? These are used in IC fabrications. We have taken one example of IC 7400, the specific IC of timer. How do we take these things? So because for any IC, what is required? There is a requirement of supply, there is a requirement of ground. Because without these two parameters, no electronic circuitry is going to work. What is required? Supply and ground. So that's how we gave supply and we gave a ground. Next thing, these are the gates. So where actually we are using these gates? We are using for a specific functions. This is our timing sequence we do have 7400. For that purpose, this is useful. So NAND gates. So the main important of here is how do we take NAND gate and its equivalent functions. So what is the meaning of that? You had two types of basic gate. Three types of basic gates are there. One is NOT, and OR. So these gates, how do we implement? By using the NAND gate. So that point here I am explaining. So that means NAND gate is first thing is what? It's a universal gate. Universal gate, what we are saying? Because widely these gates are useful in all types of designing, in every way. Because we prefer with OR gate, somebody like AND gate. So it's not about the preference, it's about all gates needs to be designed by using the NAND gate. So we are taking first all NAND inputs, what we are taking. Suppose this is which gate? This is NOT. The same NOT function you can get if you take single input and you are connecting with one, what is this? NAND gate. The same next is what? We decide when we design this thing A and B. Likewise, we are using AND gate. How do we get AND gate? AND means A into B. So this A into B, you can take two NAND gate in series and will connect with the help of De Morgan's theorems. How do we get this thing? See here, AB. What is a NAND gate? Truth table, A dot B whole complement. Again, if we pass to the next one, I'll get A dot B whole complement with complement. So I can convert that by using De Morgan's law. I'll show you these problems of this one. How do we use it? This thing, as of now you remember NAND gate, using AND gate if you want to do it. So we do have one AND gate. We'll try to connect two NAND gate in series and we'll find its equivalent functions. That means the same AND gates we can get it by using this way. Likewise, we do have OR gate. So how do we get OR gate? OR gate means A plus B. So in order to get the OR gate, we'll take two parallel NAND gate, A complement, B complement. That two parallel we pass to one more NAND gate. Then here also A plus B, here also A plus B will get. How do we get that one? By using De Morgan's laws. How do we take that De Morgan's law? Here A complement, B complement. So A complement, B complement, again we are connecting with one more NAND gate. That means whole complement. So by applying De Morgan's law, what will do it? A dot B whole complement is A complement plus B complement. So here A complement double. So A double complement, B complement double. That is B double complement. So A plus B we left, A double complement will be removed and B double complement will be removed. We got A plus B. So what conclusion you can take from these things? It's quite rotating in your mind all these things. But as of now you remember, if you have one NAND gate, that is similar to one NOT gate, because NAND gate is also give complement, NOT gate is also give complement. Similarly, if you do have NAND gate, what is that NAND gate? This thing, this NAND gate, we are taking two series. Series means it's similar to AND. If you're using 3 NAND gate, it's similar to OR. How do we connect that one? 2 are parallel, 1 with series. So this is how your NAND gate functions is going to be worked. So this is how this complete functionality we will see with the problems. Next, we do have the same function for NOR also. That NOR also I will show you when we get this topic. So what is the meaning of multiple inputs? What is the meaning of that extension? So we have taken, see here example, x plus y plus x. That means here also 2 variable, here also 2 variables. So this is nothing but more than 1. That means it is a multiple input. So we had here 3 variables, that is also multiple. So in addition, OR gate functions, or in multiplication, AND gate functions, both are same. Next, multiple input implementation, these functions and working of it. So this positive and negative logic also we do have, that we will continue completely in the next class. How do we get this thing? All the types of logics. So what you have covered in today's class, we covered major topics of 2 things. One is the KMaps, next is the logic functions. So in KMap what we have discussed? We have discussed the first thing is the history. Who I explained that one? That is a Karnaf, a name of the person who described it. So what he explained? He explained about the square boxes. Each square box represent one mean term, one max term. Then we have seen its combination. Then we have see the 2 variable KMap, the graphical or pictorial diagram, 3 variable and the 4 variable. And then we have discussed the logic gates. The same AND gate, how do we represent that AND gate into respective functions like basic gates OR, AND and NOT. Thank you for today's class. Have a good day.